Hi, I'm Shaul. I have recently discovered a YouTube channel I really like. It's a channel belonging to a bloke from rural Germany. And he happens to be, like me, obsessed with the rendering of the image. He had a lot of experience with all the large and medium format cameras that excel in creating those lifelike, rich images. And he tried to replicate this look on modern cameras, digital cameras. On his channel he compares a lot of lenses, but also some cameras. And it discusses the impact of the gear he uses on the look or the perception of the photographs made. Thorsten Geh, I hope I pronounced his name correctly, is a bloke I like. He has a keen eye, but more importantly, his heart is in the right place. He mainly asks questions rather than developing hypotheses and theories to explain his findings. This is perhaps my background in science that makes me try to explain things rather than just observe. And I'm cursed with it. Anyway, Thorsten observed that some APS-C cameras have a more poppy look than others, even when mounting the same lenses on them. For example, he noted that the old Nikon D7000, it's a DSLR made maybe 13, 14 years ago, creates a rather flat image, no matter what lens you mount on it. The much more modern mirrorless Sony A6700 is a little bit better, but still it creates flatter images than another camera, which is the Fujifilm X-T3. Now, this has nothing to do with pixel pitch. The Fuji and the Sony use very similar sensors with very similar pixel pitches, but still there is a difference in the appearance of the images. I tried to think of reasons why that might be. And I absolutely trust Thorsten. He has a keen eye and a lot of experience. So I have no reason to doubt his observations. A sensor accomplishes a rather straightforward task. It has a lot of photodiodes. Those are tiny devices that absorb light and convert the light into electric charge. And that electric charge is then converted to a number through an analog to digital converter. Then the number is transmitted to a buffer, and an image is created out of all those light intensities. Now, on the surface of the sensor, there is a color matrix that creates a complex mosaic that combines the specific color filter on top of the photodiode and the light intensity. And the rest is only math. Complex calculation is performed in which adjacent tiles of this mosaic are mixed, and the information is interpolated to create the image that is presented to us by the camera or by a raw developer. This process is common to all imaging sensors in all cameras. The efficiency of this process, especially the fill ratio of the sensor and the efficiency of the transfer pipeline, determine things like noise and dynamic range, but those don't have much to do with the poppiness of the image, which is basically created by the treatment of light upstream to all this number crunching. So we already saw the impact of the optics on the look of the image, on the three-dimensional perception photographic image may offer. And I will come back to it later to further discuss it. However, my hunch is that the layer of glass that covers the sensor has an impact on what the final image would look like. The electronics of the sensors, photodiodes, are not exposed to air. They are tightly covered by a thick or thin glass layer, which is called the sensor stack. That layer has a few functions. First of all, it offers physical protection of the delicate electronics. Second, it contains filters that block unwanted wavelengths from reaching the sensor and influencing the light captured by it. Those sensors are high-pass sensors that blocks ultraviolet light, and low-pass sensors that blocks infrared wavelengths. The image stack might also contain a layer of anti-aliasing filtering that blurs the image in a very subtle way to prevent phenomena like moire and other false color creating during the demosaicing. However, the level of blur is very small, very subtle. Typically, it's less than 1 micron, which is truly not, doesn't have much of an impact, considering that the smallest pixels available in cameras are around 3 microns. So it's a sub-pixel thing. Then there is a layer of micro lenses. The light has to be focused onto the photodiode, because at least in some older sensors, there was a lot of neutral area that was not able to collect light and convert it into electric charge. Nowadays, with the prevalence of BSI, back illuminated sensors, that is less of a problem, because the photodiodes are closer to the surface of the silicon. The micro lenses focus the light to the center of the pixel, or onto the surface of the photodiode itself, that does not cover the whole pixel pitch. And thus it makes the whole process of light gathering much more efficient. In modern sensors, the efficiency of light gathering is close to 100%. So those tiny little lenses with a diameter of only a few microns have to be very efficient, and they are. The difference in the rendering of different cameras might be due to the actual refractive index of the glass in the sensor stack. That, combined with the thickness of the sensor stack, that is quite varied. For example, Leicas are known to have a very thin sensor stack of less than 1 millimeter. On the contrary, Micro Four Thirds is known to have a thick sensor stack of around 4 millimeters. And most other systems have a sensor stack that is about 2 millimeter thick. The refractive index of the sensor stack might shift the angle of the light hitting it. And by doing that, it slows down the transmission of light and lets the glass extract more tonal nuance. In the same way, the light passing through the lens changes its angle multiple times. And the more change in the angle, the more tonal nuance is extracted on the different color channels, and the better or more poppy the final image looks. There is no information publicly available about the sensor stacks used by different manufacturers. But as far as it goes, this can be the only explanation for the different renderings of different cameras with similar sensors. To demonstrate the relation between tonal nuance and the depth perception of the image, I would like to go back to some examples shot during the test I made with 35mm lenses. On the screen you can see 3 images taken by 3 different lenses. On the left is the light lens lab 35mm f2, which in a survey I made achieved a moderate poppiness score of 2.65 out of 5. In the middle is the image, or a crop of the image, made with the Nikon Z 35mm f1.4. That image achieved a little bit higher poppiness score of 2.83. And on the right is the same crop made from an image that was shot with a more poppy lens, at least according to the survey. The Nikon 35mm f1.4G. The poppiness score of that image was 3.74. Now, as you can see, there is a clear difference in the amount of tonal range represented in each crop, where the gamut of the green colors in the left image is much more limited than the gamut on the right image. There is more separation between the leaves on the 2 right images than on the left image. And also the bamboo fence behind shows quite a noticeable difference in the nuance, where the right image made with the Nikon 35mm f1.4G shows more variation. According to my hypothesis, part of the effect, the 3D pop or rendition of 3-dimensionality, stems from light dispersion, which means there is a separation between the different components of white light created by the optics. The more separation, the more tonal nuance in the different color channels. Unfortunately, that also means that poppy images will always have more color fringing, which is correctable. I was quite surprised to see how well modern raw developers can diminish this color fringing. And diminishing color fringing does not really affect perception of depth from the photograph. They address only the high contrast parts of the scene that really show a lot of fringing. This is that Light Lens Lab 35mm, and as you can perhaps see, it has a strikingly yellow or orange coatings. Now, this goes a little bit against the grain, but the color of the coatings represents light reflected from the lens, rather than light transmitted by the lens. This lens has quite a cool color signature, because a lot of the warmer colors are reflected by the coatings, and they do not reach the rear of the lens and the sensor itself. That causes a partial dispersion made by the lens. It is not full spectrum. It reduces the effect of dispersion on the look of the image, and creates a flatter image. Compare it to the Nikon Z 35mm f1.4 that does not have coatings with a strong color cast. It's a much more neutral lens, so it allows a full spectrum dispersion that passes through the whole dimensionality of the scene. Alas, the understanding of this phenomenon, of how readily you can perceive the three-dimensional nature of a scene from a two-dimensional photograph, is an ongoing process. The underlying principle is that we need lenses that imitate the human eye in their optical characteristics. Right, that will be all for today. If you like my channel and find it helpful to you in any capacity, please consider buying me a coffee. There's a link in the description. It's a nice gesture between gentlemen. So thank you for watching, and see you again soon.